to do. Okay. So I just think stars are beautiful. This actually is the constellation Orion. And Orion is a good constellation because it's got kind of an assortment of colors of stars. Remember we talked earlier about how stars have different colors. Okay, you can see a yellow one, a blue one, kind of a reddish one here. So this is Orion. You know it's Orion because actually, I don't know if you can see those 3 stars right there. That is his belt, okay? And then these 4 stars are kind of his, well, it's kind of, I think of his toga. It's kind of like there's his shoulders and there's kind of his knees of his toga. And this cool thing right here, this beautiful thing actually is the Orion Nebula. Orion Nebula. And actually you can see the Orion Nebula just with binoculars. So it's very pretty. Okay, but we're going to talk about general characteristics of stars. So one of the things about a star is you need to know how bright it is. Now there's different ways to think about brightness. Okay, this actually is the light bulb way. So like when you go to pick out a light bulb to put in your light fixture, you look at the wattage, right? The wattage of a light bulb is basically saying how much power it's going to radiate per second. Okay, so we actually talk about wattages of stars. Okay, same thing. Now there are different ways, like I said, to talk about brightnesses of stars. Okay, the first way we're going to talk about is actually something called the apparent brightness, and it's a lowercase m. Okay, so apparent brightness actually, it's shown here, is, I like this little figure down here. Apparent brightness would be basically how that star, and actually I think this is our sun, okay, how bright does that star or sun appear? Just basically how much light is hitting us, okay? That's its apparent brightness, the lowercase m. And there's another brightness scale with an uppercase m coming up. But one of the things we know about brightness is that actually the farther you are away from the source, the dimmer it is. So like for instance, you know, if we were to put a candle, right here and have a light meter, okay, it's got a certain luminosity, okay, it's constant. But if I step back and I have my light meter, it's going to read less light. If I step back further, it's going to read less light. And you can just see that visually. Okay, you get too far away from the light and you're like, oh my gosh. Basically that light is so diluted. And this figure over here is showing you kind of the dilution of light. Basically it says that light is going to go in all directions, okay? Light illuminating in all directions. And for every little, you kind of see these 3 little orbs. For every little distance r, there's r1. Okay, this would be r2. Okay, this would be r3. Okay, for every distance it steps back, it's diluted a square of the distance that it is. Okay, so it's called the inverse square law, actually. So light becomes diluted. So we have a little bit of an issue looking at how bright a star appears and kind of backtracking to how much light it's really putting out because of that distance thing. You're like, you know, it could be bright because it's close to us, or it could be bright because it's really pumping out the energy. So how bright a star appears depends both upon its energy it's putting out, that's luminosity, and how close or how far away it is from us. Okay, so like I said, put another way, you know, you really can't say a lot. Just, you know, you can enjoy the stars in the nighttime sky, but you really can't say a whole lot about comparing them because you don't know what the distance factor is. Okay. So brightness. Remember, brightness is what it appears. Okay, sometimes that's called apparent brightness. So actually, I'll put the word apparent here. I can never spell apparent. That's totally butched, but hopefully you get the idea. Apparent brightness, and that was the lowercase m. Okay, apparent brightness, actually you can calculate apparent brightness if you take the luminosity, which is the energy pumping out, and divided by 4 pi, of course, 3.14, blah, 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 4 pi r squared, okay? We can rearrange that, and if we know the brightness and the distance, we can backtrack and get the luminosity. So it's just like, you know, it's just a little algebra problem. So we do have some possibilities in getting at, for instance, the luminosity, the energy that a star is putting out. Now it's kind of cool. You would think that stars are just stars, right? Stars all do the same thing in their cores, right? We talked about in the chapter on our sun that our star, the sun, is actually creating energy by nuclear fusion. It's all the same. No, it's not necessarily the same. Okay. Then the last thing is if we know the luminosity and we know the brightness. Remember, brightness is just as it's gauged from our perspective. Then we can get to the distance. And who would not want to know how far a star is from the Earth? I mean, that is a cool thing to get to. Okay, so we can, like, if we know, it's the whole, you have one equation, and if you know two, there's three variables, and if you know two of those three variables, you can get to the third sort of thing. So one of the things we talked about, when we talked about early on, coming up with this concept of how planets orbit the sun, how the Earth is orbiting the sun, is this idea of parallax. And remember what parallax is that was the one where you hold your finger in front of your nose, and you kind of close one eye and close the other eye, and you look at your finger move against the background. So parallax actually will occur if you have something relatively close by, and you're kind of changing your point of view. And so that's why people said, well, the Earth can't be orbiting the sun because we'd see parallax in the stars. And actually, this is the same figure I think we looked at before. There is parallax in the stars. So remember how this works is these are seen 6 months apart in January and July, okay? And the awesome star is, you can't see it very well, but the awesome star is that kind of pinkish star right there. That pinkish star moves against the background stars, okay? And why? Because that pinkish star, I guess it's kind of pink-purple, is relatively close. It's like your finger, okay? So the Earth is here, then the Earth is here. So we can, if we're trying to see how far away that star is, actually how much it moves against the background stars, it creates what we call a parallax angle, and we use that parallax angle to get a gauge on its distance. Or astronomers can anyway. So basically, the closer the star is to us, the more parallax you'll see. And you can, again, do that with your finger if you want to. Kind of do here, blink one eye and one eye, okay? And then move your finger a little bit farther, blink one eye and then the other eye, and then move it even farther. And you'll see it jump less the farther it is. So the thing is, at some point, we can't use this technique to see, to gauge the distance to the star, okay? And I've heard it described, the better the telescope you have, the more detail you can see, and the more you're likely able to see that little bit of wiggle as we change 6 months apart. But there's definitely, we have stars that are farther from us than 1,500 light years. And that's kind of the threshold of, you can't, if something's farther than that, there's no way. You can't see parallax, so you can't use this method. So luminosity is like your light bulb. Okay, luminosity is wattage, the amount of energy that the star is putting out. And this is just kind of a random question, but over here at the side, you can definitely see the kind of different colors in this set of stars. Definitely see greens and reds and blues and oranges. And it goes back to I think it was chapter 4 when we talked about like the color of something is actually an indication of how hot it is. We're going to see again, red is cooler, blue is hotter. Okay, the Roy G. Biv, red is longer wavelength, blue is shorter wavelength.
I got a question.
Mm-hmm.
Is it just me, or could that very easily be mistaken for black sand beach?
I've never been to a black sand beach or the black
crazy.
Sand beach.
It's crazy. Hawaii.
Sounds cool. I don't think your author would throw this in and make
It's
it
true.
a beach instead of stars.
It's true.
Last week when we were here, we talked about our sun, and I kind of told you ahead of time that we would be comparing other stars to our sun. So the luminosity of our sun is going to be an L with a lowercase sun. Okay. So with regard to other stars, okay, remember this is kind of normalized for distance. That's to say that distance has nothing to do with luminosity. Luminosity is you visit the star and you measure how much energy it's pumping out. Okay, so in our say universe, In our universe, they tend to be somewhere between 1 times 10 to the 6. So remember how that works is that would be 1 with 6 zeros. 1 million, okay? 1 million times the luminosity of our sun versus 0.0001 times the luminosity of our sun. Okay? So that's kind of what we're looking at. That is the energy these stars are pumping out. While I'm on this, doesn't it seem like those would be hard to see? Yeah, and they are. But what we're going to see is there are a lot more, M-O-R-E, there are a lot more of stars that are in that ballpark than this ballpark. Less or fewer. But we see the brighter ones instead of the dimmer ones. Makes sense? Well, that's a luminosity. So apparent brightness, little m, what it appears to be. That's what we've been talking about, apparent brightness. Well, I'm going to put, it seems like a kind of a random scale on it, okay? And it dates back way back when, back in 190 to 120 BC. And I like to think of, let's see, Hipparchus as like laying down on the ground in his nice dark Greek skies and looking up and saying, that is the dimmest star I see. I think I'm going to give that a +6. That's the dimmest star I see. I'm going to give it a +6. Okay? And that's the brightest star. I'm going to give it a +1. And somebody would be like, you know, Hipparchus, you really could have made it easier for people if you did it the other way around. So dimmest, okay, brightest. So you're kind of tracking with that. So that was way back when. Now, he was just looking at stars, and he didn't use the scale for the moon, didn't use the scale for the sun. I'm going to show you those values here in a minute. But he kind of started something that we still use today.
We haven't thought of a better way to do it.
I don't know. But there must be something
Maybe
to
it's
it.
just like a tradition thing.
Must be. It's like cutting the end off of your ham to make it fit your oven, then you get a bigger oven, and then you still cut the end off of your ham, because that's the way everybody did it. But the thing about the brightness scale, the whole +1 to +6, okay, in Hipparchus, is it's not a linear scale. It's actually log base 10. And so a step of 1 is a factor of 10. So that kind of makes life a little more interesting. So like I said, you can imagine since then, if we're going to apply the scale, which we do, we kind of need to basically go less than 1, the things that are brighter than +1, and we need to go higher than +6, things that are dimmer than +6. So whenever we get a chance to, if I look at the internet and I find that there's going to be an International Space Station pass, it will give us the magnitude. It'll give us little m. And if it's like -1.3 or something like that, I'm like, dang, that's worth making an effort to go see it. Okay? If it's like +6, +5, you're like, that's not going to be much at all. Because you guys know that if you have like light pollution from your city, you know, or town or whatever, you really can't see those. You can't see a +6 even. All right, so those sky maps that I've given to you, a few of them anyway, I'll get one out for November next week. No, 2 weeks. But actually that scale that they use for brightness, that's this scale. It's apparent brightness, what it appears to be. Mm-hmm.
The third from the bottom bullet point.
Mm-hmm.
I feel like that's backwards. But this whole thing is
Stars,
backwards.
for stars dimmer, we must use negative values. It is backwards. And there will be a test question, and it'll probably be multiple choice. It'd be like, which one's brighter, a -1 or a +1? You'd say -1. Yeah.
As long as I don't have to actually do logarithms.
No, you're fine. You're fine. So this is actually, you see, these would be all apparent brightness, okay? Apparent brightness of +30. Well, that's really dim, right? Apparent brightness of -25. That's really bright. Well, here we go. The sun, its apparent brightness, -26.7. Never look at the sun. That is pretty good. Okay. A full moon, -12.6. Venus, negative 4.4 at its brightest. Sirius, and actually we looked at Orion, and Orion is really cool, and the constellation Orion actually has a little dog constellation, which is Canis Major, big dog. And in Canis Major is this really bright star Sirius, seriously, okay? And it's a negative 1.44, pretty darn bright. Naked eye limit, +6. Binoculars bumps it up to a +10. Again, it kind of depends upon your viewing conditions. Pluto, +15.5. So you're not seeing it with binoculars, right? No. What's that? Telescope, yeah. And the Hubble Space Telescope, the HST that orbits the Earth, okay, it actually can image objects that are an apparent magnitude +30. Okay, so that's pretty good. Okay, so that was all little m, little tiny m, apparent brightness, or brightness. Apparent brightness, the same thing, little m. Big M is what we call, or what I call, and I'll kind of try to link it to in case you see different words in your textbook. But it's called, instead of apparent brightness, it's called absolute magnitude. Magnitude just means kind of scale. So absolute magnitude, actually it's absolute brightness. It's basically, I'm going to try to describe this to you, but basically you can kind of almost consider visiting that star, well, I say this, not going to the star, but going, and I don't think I have a slide to, yeah, I do. If you don't go to the star, you go 10 parsecs away. Doesn't that sound like a Star Trek term? Yes. Okay. So you go 10 parsecs from the star, okay, which is about 32 light years, because 1 parsec is 3.26 light years. So about 32 light years away, and you stop, and you look at the star, okay? And whatever it appears its brightness, that's actually its absolute magnitude, capital M. So what it's doing is kind of what we say normalizing the effective distance. Because we don't like this whole, we need to remove the effective distance so we can compare the stars. So absolute magnitude is as if you were about 32 light years from that object. Okay, so for instance, let's see, our sun, which was like negative 26, our sun, which is negative 26, right, on the apparent brightness scale, it is a positive plus 4.9 if you moved it 10 parsecs away, which I would not suggest because that would be very bad for life on Earth. Okay, because a light year's really far, okay, and 32 light years.
This is 3.2.
Yeah, but it's 10 parsecs, so take it sense.
Yeah. Yep.
I struggled with that at first. I was like, wait a second, we're shooting 32.
So anytime you see anytime in astronomy you see a capital M, it's like in chemistry we have a lowercase m and a capital M, just drives me nuts for molarity and molality. So in astronomy you have a lowercase m and a capital M, and they both deal with brightness. The lowercase m is just as it appears, and the big M is like putting it a certain distance away. It's weird to think of all these stars lined up on the same line, and you're just kind of picking off how bright they are. That's kind of how I picture it in my mind. But the cool thing, scientifically speaking, about this particular brightness, okay, absolute brightness, is since we remove the effect of distance and we're all objects are on the same playing field, we can relate absolute brightness, okay, or absolute magnitude with its luminosity. Does that make sense? Luminosity is the amount of energy it's pumping out, okay? And if we all go, 32 light years away, okay, then that's going to be all the same distance. So we can actually go lock and step, okay, absolute magnitude with luminosity. All right. So this is a bit of review. I guess it was chapter 5, not chapter 4. So the whole colors of stars thing, okay. I don't know if you remember this figure. These are radiation curves right here. These are 4 different radiation curves. Oh, actually 5. I forgot about the human one down here. So basically, we talked in that chapter about different types of energies, different types of electromagnetic radiation. Here we have ultraviolet and infrared. So here we have short lambda, and here we have long lambda. Is that bringing it back, bells? Okay. Short wavelengths are high energy, high E. Long wavelengths are low E. Okay. So that's kind of what we have going on here. So everything kind of sends out its own little band of energies. And a human's looks like this. Okay. And then, but more importantly, we talked about stars. And these were actually remember our sun is like 5,800 Kelvin? 5,800 Kelvin. There you go. That's kind of what its radiation curve looks like. A hotter star, if its surface is more, instead of 6,000, it's 15,000. Okay, basically two things happen. We talked about the whole thing jumps up and it moves over to the left, which is the shorter wavelengths. Okay, a cooler star, surface temperature, 3,000 Kelvin, it squats down and it moves over to the right, longer wavelength, lower energy. Okay. So, something else with regard to stars. This is, and we'll talk more about this on a later slide, where this came from a little bit. But, how do I say this? Well, this will work. Okay, over here, you see these temperatures in this third column, excuse me. See this? Okay, those are all surface temperatures. We can find the sun right here. The sun is what we call a G-type star. So this first column is very important. This first column is how we classify stars. Okay, and I've got a little mnemonic device here. Oh, be a fine guy, kiss me. That is right there in the first column. Oh, be a fine guy, kiss me. The 7 different types of stars. I know it sounds really hokey. But the 7 different types of stars actually kind of line up with colors. So O's are hottest, so we know right off the top these are going to tend to be blue for the O-type stars. M are the coolest, and these are going to tend to be red. Okay, and then anything in between. Okay, so that's kind of a look at that. And then that last bit over here, this over here, I don't know if you recognize, those are all absorption spectra. Okay, so each line is basically looking for, or each spectra is as an example of that type of star. Okay, and I'm going to tell you, I couldn't do it, but basically there's going to be a picture coming up of a bunch of ladies that actually, I'm going to use glasses here. This is my supposed to be look. Those are glasses. Basically, a bunch of ladies looked at these, okay, and categorized stars based upon their spectra as being one of these types. So I think that's pretty cool. So there's 7 spectral types. O, B, A, F, G, K, M. And then one more time, O's are the hottest, because this is important. Okay, and M's are the coolest. They're the coolest. And we're about a G. So right away, can you kind of see we're a little bit on the cooler side of middle of the road star? Cool. So how hot are the surfaces of stars? Now, we're not talking about their cores, because their cores have to be a lot hotter than this to fuse either hydrogen or helium or whatever they're fusing. So other stars tend to be, the coolest ones are about 3,000 Kelvin. We saw a map kind of what that radiation curve would look like a minute ago. And the hottest ones are about, on their surface, 50,000 Kelvin. Pretty hot.
So these are all surface temperatures.
These are all surface temperatures, yes. Very good. Yep. Okay, so this is just another look at what we saw before. There's the 7 different types of stars kind of going across, okay? These are the stellar spectra. This slide, it's a little, not a slide, but this figure over here is a little busy. I kind of like it though. Notice what it does is from the bottom up, it's getting hotter and hotter. So of course K is Kelvin, that's the absolute temperature scale. So we have 10 Kelvin, a bit chilly, isn't it? 0 Celsius is 273 Kelvin, okay? So 0 Kelvin is very cold. Here, 10 raised to the second power Kelvin, of course that's 100 Kelvin, okay? 10 to the third, 1,000 Kelvin, 10 to the fourth, 10,000, 100,000, and 1 million, okay, Kelvin, degrees Kelvin. Now, this over here, I really kind of like these pictures, what your author has done, because it talks about what does matter do at those different temperatures. Okay, so matter at the very cold temperature, okay, it sticks together. If you're talking water, it's definitely going to be frozen. Okay, water at 100 degrees Kelvin could, I don't know if it necessarily depends upon the pressure, but as you get warmer, I'll just put it this way, water melts, so you see the snowflake go to a liquid. Okay, as you heat water up, what's it do? It vaporizes, steams, yeah. And I like what your author's done. Can you see comparing, for instance, this liquid right here, okay, with the gas? Two things, I think we talked about this before. The gas has a lot more motion, okay? And the other thing is the gas doesn't have these little connections here that the liquid does. Okay, so if you go ahead and heat up, and I can see actually this is water because it's a cute little Mickey Mouse molecule. The red thing is oxygen and the two white things are hydrogens. So if you heat gaseous water up enough, look what happens. It breaks up into hydrogen and oxygen. Okay? If you go ahead and heat up hydrogen and oxygen, okay, guess what happens? An electron leaves. When we talked about the sun, they actually talked about this kind of third phase of matter called plasma that our sun is just chock full of. Why? Because it's hot enough to basically ionize or strip away an electron. Okay? And if you heat it up high enough, okay, now they're showing actually it's just fully ionized. My point here, well, let's put it this way, and I think your textbook does it, and I don't emphasize it much in my slides, but in order to make these, and actually I think this was a test question, in order for you to get these lines, do you remember it was the electron that made them? Okay, so the problem is if you basically from here, let's see, basically, that'll be okay. From here on up, if the electron is no longer associated with the atom, you can't be seeing any sort of those things. So actually the absence of lines is an indication of it's just crazy hot. So, crazy. These are those ladies. I just think this is so cool. These are those ladies that there's one guy, doesn't he look happy? That basically, clear back then they were getting stellar spectra. Now those like the where we see the rainbow with the dark lines, that's not any small feat. Okay, basically you have to photograph the star. Well, I should say that. Before you photograph the star, you have to take the light from the star and you have to separate it out into the rainbow, and then you have to look for those dark lines at a particular wavelength. And they would like match them up into piles. Then if you read about it, you're like, how did they come up with O, B, A, F, G, K, M? How did they come up with those 7? You're like, dude. Well, like this slide says, they first started with A through O, and then actually they got their piles, and I don't know how many piles that would be, and then they started saying, wait a minute, we need to rearrange here. And so then they rearranged and came up with this O being the hottest and M being the coolest. So, and there was some overlap, so they ended up with those 7 spectral types. I think that's cool. Okay. So I don't know, I haven't mentioned it lately, but I probably mentioned that we think our, I was going to say our sun has a companion or had a companion, but probably less controversial than that. If you're out in the nighttime sky and you have your telescope handy, oftentimes you can look at what looks like 1 star, and actually it's really 2 stars, or a quartet of stars, 4 stars, okay? There's just, And sometimes it's just because of how they're lined, and sometimes they're really gravitationally near each other. That's called a binary star system.
There was a picture that came out like yesterday of two stars that actually collided.
Oh dear.
Yeah. Like they're like touching.
They're what? Touching?
They're touching. Like they're not like they haven't run into each other. They're just hanging out.
I think I've watched documentaries, and like the thing about gravity is it's a weird sort of force, and it can be actually thought of kind of making a dent in basically the fabric of space and time. So actually, they can start out and then they kind of collide. So yes,
I wish I could find it.
sounds interesting. Yeah, send me that.
If I find it, I will.
But most stars, and we're going to talk about how stars are born in the next chapter, but most stars actually have a buddy. It says half, but I think even more than half. And they don't, it's not like, well, do you remember Pluto and Charon? Okay, like here's Pluto and Charon so big that it's not like Charon does this. It's basically that they kind of do this dance. This is what we call common center of mass. That's what the stars do. Okay, they have a common center of mass. All right, so how do we know that there's two stars? Well, we have three options. Here's our three options for seeing there are actually two stars. One is just we see the two stars, okay? It's a visual binary, we say. And here's an example, okay? Sirius, Sirius is called the dog star. That's Ursa Major in, really? Canis Major. Darn it. This isn't Canis Major. This is the bright star that we saw a minute ago. It has a companion that is I want to say it's a white dwarf companion. So Sirius A, normal star. Sirius B, it's a little white dwarf companion. All right. Mizar actually is a star in the handle of the Big Dipper. And Mizar, if you have a decent telescope, you can actually see Mizar is, maybe even binoculars. Mizar is a bright star here, and it's got a rider called Alcor, I believe, Alcor. So Mizar and Alcor. Then if you have a really good telescope, you can actually split those, like this says, into each star has a buddy. So there's a little vortex. So one is that you just see them, okay? But more than likely, you need to be more sneaky than just seeing them, right? So one sneaky way, it's called a spectroscopic binary, and I'm not well, I guess so. If you see the word spectra in spectroscopic, look over here. These are the spectra, okay? So basically, what you do is, you can't tell that there's two there, but basically you're going ahead and you're creating your little spectra, and you see the spectra kind of goes back and forth, okay? That's not right. You see the spectra actually is, you see the star wiggle, final answer. You see the star wiggle, and it's wiggling because there's another star there, okay? You're seeing the spectral lines move to the short wavelength when it's moving towards you, it's a blue shift, and a long wavelength when it's moving away from you. The last one might ring a bell. Let's see what I'm saying. Remember we said, how do you find planets around other stars? This is one of the methods. Okay, so this is very similar. But in this case, it's a pair of stars. And the pair of stars might not be the same brightness. So basically, when they're facing you, okay, you don't know there's two, but you get all the most energy you can. When one goes around the other, basically this one's eclipsing this one, you get less light. When it comes around, you get a lot of light. When it goes in front, you get less light. Okay, so that's the eclipsing method. All right. This seems like kind of a repeat slide, so I'm not quite sure. There is a subtle difference. There's, I guess, a big difference. Okay? There's true binary, and that's what we talked about. Basically, two that are gravitationally stuck to each other or hanging out together. True binary. And then there's the optical binary. And the optical binary is just that they look like a nice little pair of stars, but they are nowhere necessarily near each other. It's just our kind of line of sight. Okay? So sometimes at the observatory, they'll say, some people really like binary stars. I don't know. And they'll get them in the telescope, and they'll be like, now, is that a true binary or is that an optical binary? I'm like, does it matter? They're beautiful. Okay. So we talked about kind of the range of brightnesses, the range of luminosities. What about masses? Well, we can get to mass. You're like, how would you weigh a star? Like, I have no idea. But you do. Do you guys remember this? Let's see, I put this, it seems like maybe it was in other class. We said, or Newton said, that the force of gravity is related to the gravitational constant times the mass of each object that's influencing each other divided by the distance squared. Okay? So basically, you observe, you can use this to get to the masses of the stars. So, do you remember in a minute ago I said basically that stars orbit a common center of mass? So the stars are moving, okay? And you can look at that, them orbiting, and get a fix on the force of gravity, and to get the fix on their masses. Okay, so the mass of our sun is big M. Seems like big M was magnitude. Anyway, this is mass, not absolute magnitude. The mass of our sun, okay, compared to other stars. And we actually need to say, why is there a limit on how big a star could be or how little a star could be? So to me, this is an important limit. Okay, an object that is less than, let's see, would be 8%, less than 8% of our sun, okay, it can't become a star. Okay, anything that's more than 100 times the mass of our sun, it's too big. Okay. All right. HR diagrams. Gotta love them. Now this is cool. Two scientists in two different countries about the same time, we're looking at the stars and kind of mulling over how can we understand the stars more. Scientists are great at using charts, graphs, to kind of throw their data up. And there's something called a scatter plot. Okay? And so the scatter plot that both of these guys did, and you're going to see a few of them coming up, okay? But basically they took, like this says, stellar luminosity, okay, and I'm going to make an XY plot here. Okay, stellar luminosity. Let's see, just put a capital L for luminosity along the y-axis. And along the x-axis, they put stellar type. Okay, and do you remember a little bit ago, 7 stellar types, O, B, F, fine, guy, kiss me. Okay? And here, just for kicks, I'll kind of make sure we're all on the same page. The L, this is actually increasing luminosity as you go up. When they did that, they actually found some patterns. So these X's are going to be stars. They found, in general, not so surprising perhaps, that the hot ones, so we said O types are hot, didn't we? We said M types are cool. What they found was that the hot O-type ones had high luminosity. You're like, I could have told you that. Okay? But they were really excited. Each one of these represents a star. They were really excited that actually it made sense. It's kind of a line pattern. Scientists get excited about lines. Go figure. So what this says is actually the cooler star, the cooler the star down here, actually it has low luminosity. So that's how that works. It's even cooler than that, because here in a minute when we get going, I have made it very simple. We see a cluster of stars here, we see a cluster of stars here, we see a cluster of stars here, okay? And so actually it's a little more complicated than I've made it. But that's an HR diagram, and 2 people came up with it at the same time. So here's your HR diagram, okay? So like I said, across the x-axis is the types of stars, the O-type stars, and the M-type stars. The y-axis is luminosity. Okay. And it's a scatter plot. It's definitely a scatter plot. And they look for patterns. And that line that I was saying, can you see that line right there? Okay. And then we have kind of a group of stars up here, 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 and there. So an HR diagram is a way of kind of evaluating, we'll talk more about HR diagrams, the situation with regard to a particular star. I think I've already mentioned this before. Did I mention the word main sequence before? Because actually, it's superimposed on that. No, not yet? Okay. Actually, our son, I think I did. Our son is actually main in its stage of life, you know, called main sequence. So our son is there. All right, that's an HR diagram. And this one, oh my gosh. This one is just kind of talking you through an HR diagram. It's a little figure, can't see it very well. Okay, so our son in the OB Fine Guy Kiss Me, okay, we said our son was a G, which is cool. And I don't think I mentioned it, but it was on my slide, that we take those 7 major ways to classify a star, and we give it a number, like between 0 and 9, and ours is a G2. We can actually add something else to its classification. We can classify it, and this actually involves the HR diagram. We can classify it as a Roman numeral 1, 2, 3, 4, or 5. And our son is a G2-5 main sequence. So these groups, let's see, these groups actually are not on the line. They are in the upper, let's see, upper right of an HR diagram. It just simply means that that star is doing something different other than being a main sequence. I will tell you that these guys are aging, basically. All right. Stars on the main sequence. Okay. So those clusters that we saw here, now this HR diagram doesn't have that or here, okay, but those are different stages of their lives. We'll talk more about, in this video you'll hear the word main sequence in this video we're going to watch. Okay. Our son is in that stage of life. So up here, actually, we didn't have a, actually up here we said that our sun is fusing hydrogen to form helium. That's exactly what our sun is doing. And anything on the main sequence, that's exactly what they're doing. Okay, so when we evaluate where a star spends its life, actually most of its life is at this stage. So most stars are main sequence stars. And this actually goes back to what Hirschsprung and Russell found right off the bat. And I'd be like, I could tell you that. They just found that the most, well, I guess not. I guess this isn't what they found. But the hottest stars, we said that would be O, right? Actually, they are the most massive. The hottest are the most massive. Okay? And the dimmest ones, the reddish ones, are the coolest. Cool. So it's all kind of consistent. Of course, the coolest would be M. That's kind of what we've been saying. So this actually, you'll hear this in the video. They'll hit this quite big. And you cannot, I bet you cannot see this very much, okay? But this right here says how long they'll live. The thing in green. So, for instance, here's the sun, okay? And how long is it going to live? It says 10 to the 12th. 10 to that. No, it must be 13th. No, 10 to the, let's see, what's 10 billion? So million is be 10 to the 7th. Final answer. Well, down here this says, I guess I'll do it this way. This star down here, kind of drawn to scale, very small, this will live the longest. How's that? Live the longest. Okay, this guy right up here, okay, he looks like he's got a lot going on for him, but actually he's going to live the shortest. Live the shortest. And when I say live, I'm basically saying well, it'll live the shortest, but it'll be a main sequence star the shortest amount of time. And this will be a main sequence star a very long time. The more massive the star, the faster it will live its life. Kind of sad, kind of sad. So in the HR diagram, must be coming up here in a minute. I guess not. In the HR diagram, there were, if you look at the upper, above the main sequence, there's those things, the circles I've been drawing. Actually, those would be your giants and supergiants, okay? And white dwarfs are kind of down there. Let's see. Let's see. Let's do this. Let's take a break, and then we're going to finish up this, and then I'll cue up the movie, and we'll do it that way, okay? 10-minute break.